So hello everyone, this is Professor Kleinium, your favorite AP chemistry teacher, and this podcast is dealing with the subject of electrochemistry, and this is a specific handout that I gave in class that I thought maybe we can save some time in class if I just try to explain it here. And so this one is about 15 questions long. And so I'll try to hurry through this as much as I can, but you can't go too fast on some of this, so here we go. Alright, so when you have half cells A and B are used to form the galvanic cell X. So we're forming this galvanic cell here, labeled X. And notice it's two chemicals involved, that would be A and B, that relates to the zinc and the copper, so see how it's written. And for this problem, they're asking us to figure out what is this unknown right there. Well, this is an easy one because both of the values we need are given to us up here. The main thing to look at here is the way this is written, which one is the oxidized one and which is the reduced one. The zinc here goes from 0 charge to +2, that's oxidized. Copper goes from +2 to 0, that's reduced. So using my little formula for oxidation and reduction, I take the one that's being reduced and then I subtract off the one that is oxidized. Okay, so the numbers involved would be, I noticed the reduced one, copper, is 0.34, and then minus the one that is oxidized, that's the zinc. I'm going to put this in parentheses to keep the signs all happy here. Negative 0.76. So this is where I get those two numbers. Well, now as you see, if you're subtracting a negative, that's the same thing as adding a positive. So really I'm going to add these two numbers and I get 1.1 volts. Yeah, that sounds like the answer is D here. Okay, very good. Problem number 2. So half cells B and C are used to form a galvanic cell Z. So here we're talking about galvanic cell Z. And I'm going to use these two chemicals, copper and lead, as you can see here, right here, copper and lead. What is the standard cell potential? So the question here is, what is this number? Alright, so then what are the challenges facing us? We need to figure out what both of these are. They don't give us lead here. That could be a challenge, except that we can deduce it from this second one here where they do give us an answer, 0.63. See, we know that it's 0.63 for this cell right here, in which zinc, being the one oxidized, is the one that goes behind. That's negative 0.76. Okay, I'll put that in parentheses to keep the signs happy. And the lead we don't know, so it's really X minus a negative or plus a positive 0.76 is equal to this is equal to a positive, so see that this is all part of the equal sign here. This is equal to a positive 0.63. Alright, so do a little algebra on this. I discovered that the lead is going to be a negative 0.13. It's really this number minus that number. Okay, so far so good. So what I just figured out is the number right here is a negative 0.13. Well, now knowing that, I can now write the potential for this one. I just have to plug in the numbers I see above. So see, I'm showing that the lead is the oxidized one. So that number I just got, negative 0.13, I put that in for the oxidized one. The copper we can get from up here. That's a positive 0.34, and then it is running in the reduced area, so that's correct. So I'm going to add this positive number, so it's going to be 0.34 plus 0.13. for a total of 0.47 volts. And now we have the answer. It looks to me like the answer is B. So it's a little bit of running around to get there, but that's a pretty good problem. Okay, problem number 3. Galvanic cells Y, and Z. So this is a two-part problem. Have to worry about. See that? Which of the following takes place in half cell A? So half cell A here is the zinc part. So what's going on with zinc here? And half cell A. Well, for X and Y, I'm sorry, C, that's it. It's not the Z part. It's X and Y, no wonder, because I need to worry about the zinc. Okay, so let's look at X. What's going on with the zinc here? Well, clearly the zinc is being oxidized. So oxidation is occurring in cell X for zinc. And for Y, what's going on with zinc? Oxidation is going on. So in both cases, oxidation. Is that down here? The oxidation occurs in both of them. Well, that must be the right answer right there. Because in both cases, the zinc here is running in the oxidized position. Okay. Now, here we have the amount of lead nitrate. So remember, this is the lead in the ion form is replaced with 3 molar. Just to remind you, the solutions here, the standard solution would be 1.0 molar. So that, let's say that's both for the lead, and then whatever the galvanic cells Y and Z, how it affects. So for Y and Z, all right, so this is the two we're looking at, which both do have lead in it, although it looks to me like the lead is going to go in different direction in both. So let's first of all look at cell Y here. Okay, so you see right here where it's showing the lead +2 for the Y. According to Le Chatelier principle, if you increase the molarity of this, which is what we're doing, we're going from 1 molar to 3, should drive the reaction further this direction, which is the favorable direction. That should increase our cell potential. And so for Y, the cell potential is increasing. This could be the answer right here. Let's hold on to that for a second, because it may not be the final answer. So let's look at what's going on with lead here. Here, lead is being oxidized. So if we were to increase the molarity of the lead solution to 3 molar here, then that should actually push it the wrong way. It should decrease the cell potential. So it's not going to be increased in both. It's going to be increased in Y and decreased in Z. Seems to me like the answer is going to have to be C here. Okay. What qualitative observation can be conclusively made to demonstrate this reaction is happening as written? So cell X, get this straight, for cell X, how would I know if this is working and that this is a positive E potential? Okay, in other words, E potential positive means favorable. Well, it would be favorable provided these are both running the way that they like to go. In this case, zinc electrode would be dissolving into the ion. Zinc would be getting less heavy. And I happen to notice the mass of the zinc increases. That's wrong. The overall cell potential is negative. We'll see if it's negative, it's not favorable. The copper solution in volume, that's wrong. So see, the zinc electrode should be getting smaller and lighter and dissolve. Okay, so if a chemist needed another substance to replace in half cell A with something more effective than zinc, so what that means, you'd have to find something higher on that Bowley chart for the single replacement reactions, or actually one with a more negative value here. And you know, the answer is going to be sodium. I didn't look it up, but sodium's got to have at least like -2 or maybe -3 up here. So it's really wants to be oxidized in the worst sort of way. Okay. The galvanic cell is made up of 2 half cells of aluminum and lead. Okay, so we see there the reduction potential for lead is -0.2 -0.13. That's kind of deceptive the way that's written. It's -0.13 volts. So notice that that's for the lead part. What is the standard reduction potential for the aluminum side? Well, the total, as you can see, is 1.53. Now, I got to figure out what's going on. The aluminum here is the one that's being oxidized, and the lead is the one being reduced. So, in fact, it's gonna go the direction as written here, because certainly aluminum is higher on the oxidation table than lead. This single replacement reaction is going to occur. This is a bigger bully than that. So what I would do is I'd put the one for lead in the front here, which they give it to us at -0.13, and I'm going to subtract off the one for aluminum, which they don't give us here. So that's just going to be X. Okay, well, very good then. Looking at the math then, I need to add a negative here. So when I rearrange everything, I get X is equal to -1.66. That's the aluminum side of the equation, so the answer looks to be D. Okay, so here we have a reaction. It's the same reaction as the last one we just saw. How many electrons are being transferred? This is actually kind of an easy question because remember each of these aluminums has 3 valence electrons. So you can see since we have 2 aluminums, I'm putting in here a total of 6 electrons may be transferred in this balanced chemical reaction. They're all going to go over to the lead side. So when you calculate how many electrons are being moved, just kind of figure out how many are going to go. So we have 3 leads, each one of which is going to pick up 2 of these electrons. The total is 6 electrons total are going to move. Okay, so if a solution of sodium iodide is introduced, what that's going to do is it's going to take out some of this. You're going to see some lead iodide solid produced, and as you know, if you reduce this down, it's going to have a negative effect on the cell potential. It's going to take out that, according to the Le Chatelier principle. So it should reduce the number 1.53 to a smaller number. Let's see, so the cell potential will decrease due to the form. Okay, there's the key word, is precipitate. Alright, the answer has to be D. What happens to the cell potential of the galvanic cell if it runs for 15 minutes? So if it's running for 15 minutes, the concentration of this is going to go down naturally, and so you would expect, since the reactants are decreasing in amount and concentration, that the cell potential here is going to gradually wind down, ultimately to 0 when the reaction's finished. So the cell potential will decrease. That sounds right. Which reaction below will require electrolysis? So in other words, what that means is the E potential for one of these cells needs to be negative. See, that's the key. It's going to be a non-favorable reaction. So to make this work, you're going to have to, in these 2 cells, you're going to have to add extra energy to make this work. Okay, so the ones that are going to end up with a negative potential, I think the answer was the third one here when I looked at it. See, the nickel is oxidized and the chromium is reduced. So the nickel being the oxidized one means it's going to go in the back here. Okay, and then the chromium being the reduced one would be as written here, the -0.74 minus a negative. So see, this is going to be plus a positive. Yeah, but you see, after we add these together, we still end up with a negative number. So that's the one where you're going to have to add extra energy. The delta G here is going to be a positive value. So in other words, it's not going to be spontaneous. The answer should be C. Okay, what will be the approximate value for the standard free energy? Now, delta G comes into this with a very simple formula. where you have negative N, that's the number of moles transferred, times the Faraday's constant, times the E cell potential. So now looking at this reaction, I see that chromium becomes +3, there's 2 of them, so I see a total of 6 electrons getting transferred around. That's what's going to go here for N. The Faraday's constant is 96,485. We have to multiply that in, and the E cell potential, we have to figure that out. So, as written, the chromium is the one that's oxidized. So, chromium oxidized is going to be negative 0.74. That's the one behind. Here, I'm going to subtract that off from the one that's reduced, which is the nickel. The nickel is a negative 0.25. So adding a positive, it's going to be 0.74 minus 0.25. Okay, so the answer there for the E cell potential turns out to be 0.49. So I'll plug that right in here. Take the opposite of it, because don't forget, delta G has got to be a negative if it's spontaneous. So we're going to multiply 6 times this times that, and take the opposite of it, and we get approximately a negative 300,000 joules per mole. So that appears to be B is the answer. Okay, so the equilibrium constant for the cell above is some huge value. That means that this reaction is amazingly favored in that direction. So if that's the case, what can we conclude? Well, we definitely know that it's spontaneous, so delta G is going to be negative. We also know the E cell potential is very spontaneous, so that means that's positive. So the E cell is positive, and then that's the answer is A. So now we have this redox reaction, and which of these is true? So now I looked over this before, and all of these are false for one reason or the other, but it does seem like this is true, because notice the iodine here starts out at -1, and over here it ends up at 0, so clearly the iodine is oxidized. See, the number here is actually going up. I guess that's the end of the show. So it's been fun having you. I hope you guys learned something from this.